In the last lecture, we saw the buckling of simply supported symmetric cross ply laminates. Here we will see the buckling of simply supported antisymmetric angle ply laminates. So, again we have a laminate in the xy plane. It is loaded along both the directions, and please understand these are all uniform compressive forces. So, this is Nx bar and this is Ny bar and directions x and y. Again we assume that Nx bar is 1 minus k n bar and Ny bar is minus k n bar, and all these edges are simply supported. And here, because it is antisymmetric, we have coupling between A and B matrices. So, we need to solve all the three equations, and also here for the boundary conditions we need to see what kind of boundary conditions are implemented for U0 and V0. Now, we saw before that there are different types of simple supports. Here we have seen this, here we have this kind of simple support. That means in a x face it restricts movement along x, but it allows movement along y. Similarly, along y face it restricts movement along y, but allows movement along x, and this same thing is in all the faces. So, with that, before going that, let us look at the property of these laminates. So, because this is antisymmetric, we have AXS equal to AYS equal to DXS equal to DYS equal to 0, and also we have a B matrix looking like this: 0 0 BXS 0 0 BYS BXS BYS 0. Now, if we put everything in the differential equation, we know the differential equations. We have del nx by del x plus del ny by del y equal to 0, del ns by del y, and we have del ns by del x plus del ny by del y equal to 0, and also we had del 2mx by del x2 plus del 2my by del y2 plus del 2ms del x del y, and then we have minus, if I just put everything here in terms of those k and n bar, minus 1 minus k n bar del 2 w by del x2 and minus k n bar del 2 w by del y2 equal to 0. Then what we get, the three differential equations. These are the three differential equations, and we have seen similar differential equation before also. Only thing was, in place of this we had the applied load. Now, instead of n0, let us call it n bar, same thing. Now, the boundary conditions. So, boundary conditions we have already discussed. So, at the x face we have movement along x restricted, but movement along y is possible, and w is restricted at all the four edges. So, the essential boundary conditions are this: at x equal to 0 and a we have w equal to 0 and u0 equal to 0, and the natural boundary conditions are at x equal to 0 and a bending moment mx is 0, and at x equal to 0 and a, because movement along y is possible, so we have the shear force ns equal to 0, and similarly at y equal to 0 and b we have w equal to 0 and v0 equal to 0 and my equal to 0 and ns equal to 0. So, with these boundary conditions we can assume u0 as a function of x and y as summation n equal to 1 to infinity m equal to 1 to infinity umn sin m pi x by a sin n pi y by b. Similarly, v0 as a function of x and y, we have n equal to 1 to infinity m equal to 1 to infinity vmn cosine m pi x by a into sin n pi y by b. Just one error here. So, this is cosine and w as a function of x and y is summation n equal to 1 infinity m equal to 1 to infinity wmn sin m pi x by a and sin n pi y by b. Now, these assumptions satisfy the essential and natural boundary conditions, and also if we put them in the differential equation, we can separate out the trigonometric terms. That means again here we are doing a Navier type solution. So, if I put everything in the differential equation, what comes up is this. We have inside the square bracket axx multiplied by m square pi square by a square multiplied by umn plus ass n square pi square by b square multiplied by umn plus we have axx plus axx plus axy multiplied by we have axy plus ass multiplied by mn pi square by ab, and then we have 3bx multiplied by m square n pi cube by a square b, and then we have bys n cube pi cube by b cube, and we multiply this with sin m pi x by a cosine n pi y by b equal to 0. Similarly, from the next equation we have summation n equal to 1 to infinity m equal to 1 to infinity, and then we have axy plus ass multiplied by mn pi square by b square pi square by ab, not b square, plus we have ass m square pi square by a square. Okay, so the first term has to be multiplied with umn, that was missing, umn plus we have ass m square pi square by a square vmn plus we have ayy n square pi square by b square, numerator is pi square by b square, and then we have minus bxx into m cube pi cube by a cube, so it's plus not minus, and then we have plus 3 bys multiplied by mn square pi cube by ab square, and then we multiply cosine m pi x by a and sin n pi y by b equal to 0. And finally, the last equation. So if I see the equations here, so these are negative here, so we should write minus here. So these are all minus. Yes. Now the last equation is n equal to 1 to infinity, m equal to 1 to infinity, and we have dxx m to the power 4 pi to the power 4 by a to the power 4 plus twice of dxy plus 2 dss multiplied by m square n square by a square b square, plus we have dyy multiplied by n to the power 4 pi to the power 4 by b to the power 4. So this entire thing is multiplied by wmn, and then we have minus bxs x. So if I look at this equation, so from this equation we have minus bxs, and we have here minus bys. So minus 3 into bxs and then we multiply m square n pi cube by a square b, so which comes from this term, and then we have minus bys minus so plus bys, and for that we have mn cube n cube, only n cube pi cube by b cube. So this comes from this term and this term, and then we need to write the same thing for the other terms. So here we have minus bxs del cube v by del x cube, so bxs m cube pi cube by a cube, and then we have that comes from this term, and then we have this, so minus 3 bys minus plus 3 bys mn square pi cube by ab square. So here we have to multiply that is missing, that umn. So we have to multiply umn here, and we have to multiply vmn here, and finally the sum is equal to 0. Now what we can see here is we can get 3 equations for each combination of m and n, and at every equation we can say that the trigonometric term is separated out, and this cannot always be 0. So whatever is inside the square bracket, that should separately be equal to 0. Similarly here also, whatever we have inside the square bracket, that should be separately 0, and similarly here also inside the square bracket, whatever we have, that should be equal to 0. So here to complete it, let's write that sine function sin m pi x by a multiplied by sin n pi y by b, and that's equal to 0. Now so for each combination of m and n we get 3 equations, and in the so the buckling terms are also missing, so which we need to finish. There are terms which will come from this, so which that also we have to write. So that will give us minus 1 minus k n bar into m square pi square by a square plus k n bar multiplied by n square pi square by b square, and finally this is multiplied with, everything is multiplied with this is multiplied with Wmn, because other Wmn terms are already here. So this is Wmn, and then it is multiplied with the trigonometric function sin m pi x by a sin n pi y by b and equal to 0. Now we can say that whatever is inside the square bracket, that's equal to 0. So that if I combine the three equations that we get for each m and n, the equation looks like this. So here AMN is this. Similarly BMM, what we see BMN here, that is this. Again BMN is here, the matrix is symmetric. CMN is here, the expression is this. DM is the diagonal term, the expression is this. Symmetric matrix, so CMN is here also, and EMN is here, that is this, here and here. And at the last diagonal term we have FMN minus lambda, so FMN is this, and lambda contains this n bar which we need to find out, and that's a function of k. So for different k we have to set, you can get n bar also. And here R is a term that comes up several times in these expressions. R is the ratio of A and B. This set of equations has a trivial solution, UMN VMN WMN equal to 0. It's a trivial solution which we don't want. It's not desired, because trivial solution means there is nothing is happening, no buckling. But so what we want is, for non-trivial solution to exist, this matrix of AMN, BMN, CMN, BMN, DMN, EMN, CMN, EMN, and then we have FMN minus lambda. So this matrix has to be 0 for non-trivial solution. Now if I set this, this determinant of this matrix. Now if I set the determinant of this matrix to 0, then we can solve for lambda, and if I can solve for lambda, I will get to know what my n bar is. So after doing that, finally the n bar comes out as this. This becomes the expression for n bar. Within the expression for n bar, we have J1, J2, J3 appearing. So this is J1, this is J2, this is J3. And again we can get it for different values of m and n, and accordingly we have different buckling loads, and each m and n we can put back to the approximations for U0, V0 and W, and that will give us the corresponding buckling mode shape. Now let us look at a similar problem. Now here, instead of it being antisymmetric, it becomes, instead of it being antisymmetric angle ply, it becomes antisymmetric cross ply. So again the same thing, we have a laminate in the XY system, and this is X, this is Y, and it is under biaxial load. So this is NX bar, and this is our NY bar, and we know that NX bar equal to minus of 1 minus k into n bar, and NY bar equal to minus of k into n bar. Now because this is antisymmetric cross ply laminate, then in this case we have AXS equal to AYS equal to DXS equal to DYS equal to 0, and also for the B matrix we have BXX and BYY are same. So we have BXX 0 0 0 minus BXX 0 0 0 0. So with that, again if we put them in the differential equations, we get these three differential equations. Just a correction here, this term has to be multiplied with minus of BYY, and minus of BYY is BXX. So this is this. So this is the correct version of this equation. So these are the three differential equations that we get, and again we will follow the same approach. We will write u0, v0 and w as double trigonometric functions, and then when I put it here, we can separate out the trigonometric functions, and whatever is remaining we can set them equal to 0, and then we can set the determinant equal to 0 of those three equations, and then from the determinant equal to 0 we can find out n bar. We will again write the variables u0, v0, w in the form of trigonometric series. So for that we need to look at the boundary conditions, because we have to satisfy both essential and natural boundary conditions. So these are the essential boundary conditions. At x equal to 0 and a, we have w is equal to 0 and v0 is equal to 0, and at x equal to y equal to 0 and b, we have w is equal to 0 and u0 is equal to 0. So the boundary condition is of this type, and this is same for all the boundaries. So what we see here is at x equal to at the x face, so this is the positive x face, and same at the negative x face, we have displacement allowed along x direction. So that means displacement is restricted along y direction. That's why we are seeing v0 is equal to 0, and similarly at y is equal to 0 and b, at y faces we have u0 is equal to 0. Now accordingly, because x is displacement along x is allowed at x faces, we have nx equal to 0. Similarly, because displacement is allowed along y direction at y face, so we have ny equal to 0. So we need to assume something which satisfies all these essential and natural boundary conditions, and so these are the assumptions. u0 as a function of xy is equal to summation of umn cosine m pi x by a sin n pi y by b, where n goes from 1 to infinity, m goes from 1 to infinity, and similarly v0 is equal to sin cosine and w is equal to sin sine. So if I put them in the differential equations, we get similar trigonometric functions coming out, and then we can again form a set of algebraic equations where this n where we get our buckling loads as the eigenvalues, and by solving which we can find out the eigenvalues and the buckling modes, the buckling loads and buckling modes. Now again here the series are written in terms of n is equal to 1 to infinity, m is equal to 1 to infinity. In reality, we just truncate the series after some terms, and we keep on, so depending on the number of buckling modes we want and the accuracy we want. So this ends the lecture here. In the next lecture, we will talk about the energy approaches for buckling. So with this, let's end it here. Thank you.